Good evening, everyone. Tonight we're going to do an intro to solids and discuss the surface area and volume of prisms and spheres. Alright, let's start with some definitions. So first we have a polyhedron. A polyhedron is a solid that is bound by polygons. So here we have an example of a polyhedron. A face is the flat side of a polyhedron, so there are lots of faces on the top, left, right, bottom, front, back. An edge is a line where two faces meet, so here we have an edge, or up here we have an edge. And then a vertex is a point where three or more edges meet. So here is a vertex where three of my edges are meeting. I have other vertices as well in lots of different places where different sets of three or more edges are meeting. Now we have a theorem to relate all of these, so this is Euler's theorem. Euler's theorem is a formula that relates the number of faces, edges, and vertices of a given polyhedron. The theorem is faces plus vertices equals edges plus 2, which is often written in shorthand, F plus V equals E plus 2. So now let's discuss types of solids. First, we have prisms. So prisms have rectangular sides and then two parallel bases. So here this is a rectangular prism because the base is a rectangle, and then it has all rectangular sides. And then we have pyramids. So pyramids have triangular sides and then only one base. So here this is a rectangular pyramid because we have our triangular sides and then a rectangle for a base. Now, not every solid is a polyhedron, just like not every shape was a polygon. So here, these are some non-polyhedrons. So here we have a cylinder. So a cylinder has curved bases, because they're round, because they're circles. So they are not polygons, and so this cannot be a polyhedron. Same thing with the cone. We have a round base, so that does not count as a polyhedron. And a sphere is just completely round, and so that one is not a polyhedron as well. Now let's classify some solids. So solids are classified by their bases and their type. So let's have a look at our first example. So here I've got rectangular sides, so right away I know this is some kind of a prism. And I can tell what kind of a prism it is based off its base. So here we have a pentagonal base, so that makes this a pentagonal prism. For this next example, I've got triangular faces, so we know right away that it's a pyramid, and then my base down here is a triangle, so that makes this a triangular pyramid. Alright, now pause the video for just a second and see if you can do these three examples on your own. So on my first one here, I've got rectangular sides. I know this is a prism, and then I have a rectangular base, so that makes this a rectangular prism. On my second example here, I've got triangular sides, so we know it's a pyramid, but then I have a hexagonal base, so that makes this a hexagonal pyramid. And then for this last one, we have a circular base. Well, that's not even a polygon, so this one is actually not a polyhedron. So because it's not a polyhedron, it's not classified in the same way that others are, but we do know that this one has its own special name. This is a cone. Just like we have regular polygons, we have regular polyhedrons. A polyhedron is regular if all of its faces are congruent regular polygons. There are only 5 regular polyhedron, and they are called the Platonic solids because they were discovered by Plato. So the first one is a regular tetrahedron. It has 4 faces, and each face is an equilateral triangle. We have a cube. A cube has 6 faces, and each one is a square. We have a regular octahedron, so this has 8 faces, each is an equilateral triangle. We have a regular dodecahedron, so this has 12 faces, each is a regular pentagon. And then last we have a regular icosahedron that has 20 faces, each that are equilateral triangles. So a cross-section is the intersection of a plane and a solid. So here we have a cube, and I have taken this red-pink plane right here and sliced through, and you can see the little overlapping area in there. This cross-section would be a triangle. On my next example, I have a cone, and now we've taken our plane and sliced horizontally across the cone, and so then my cross-section would be that purplish area right there, the circle. And then on this last one, so this is a hexagonal prism, so we've taken the plane and cut this vertically down the middle here of our prism, and you can see the purplish area that our cross section would be a hexagon. Now let's move on to the surface area of prisms. So we just discussed that a prism is a polyhedron with two congruent parallel sides called bases. So you know those bases, the two congruent faces of the prism, they are often seen as the top and the bottom, but they don't necessarily have to be pictured that way. We know that they're just the two congruent ones. And then the lateral faces are the parallelograms formed by connecting the corresponding vertices. So here are my lateral faces. So if you've identified your bases, then the lateral faces are all of the other ones. Now, we will ask you sometimes for lateral area, and so this is the sum of the area of the lateral faces only. So in this picture here, only these vertical faces. Or you might have total surface area, which is the sum of the areas of all of the faces. And see, I put total here in parentheses because many times they will just say find the surface area, and they mean the total surface area. So that would be all the lateral faces plus both of the bases. Now, prisms can be presented to you in two different ways. You can see right prisms. You'll see here how my two bases are centered exactly on top of each other. And so the height of my prism is the same as this edge here. Versus oblique prisms, you'll see that the two bases are not centered over each other. One is shifted over a bit. And so the height here is the perpendicular height between those two bases. And so it's just like in a triangle when you have to find that perpendicular height, it's not necessarily going to be a side length. Alright, so now let's talk about a net. So a net is the 2D representation of a solid. So here I have a cube, and I'm going to go ahead and unfold this. So it's like we cut along the edges here, and so we're starting to peel the pieces back. And so here we have an unfolded cube, and so this is my net. This is my 2D representation of a solid. So all solids have a net, so there's always a way to fold and unfold each solid. Also, all nets must be connected. So like here we see how these pieces are connected. You can't ever have any floating pieces off in somewhere else. A net has to be completely connected. So now let's discuss some formulas. So first we're going to have the formula for lateral area of a prism. So lateral area equals big P times H. So where big P is the perimeter of the base and little h is the height of the prism. So really this height of the prism is the distance between the two bases. Where then we have the formula for the surface area. It's 2 times big B plus perimeter times height, where big B is the area of the base. So notice how I talked about before, our surface area is just lateral area plus our bases. So here lateral area plus the area of the two bases. So now let's discuss cylinders. So cylinders are solids with congruent circular bases that lie in parallel planes. So cylinders behave very similarly to prisms, just with circular bases. So here for my formula of lateral area, my lateral area is going to be, well, it was perimeter times height before, but we know that the perimeter of a circle is called the circumference. So my lateral area is circumference times height. And then I can, if I would like, go ahead and plug in 2 pi r. So lateral area is 2 pi r height. And then for surface area, it's 2 times big B plus circumference times height. So that's going to be 2 pi r squared plus 2 pi r height. So just as a note that these are the same formulas as a prism, we've just plugged in area of a circle and circumference for the big B and big P. Now let's talk about volume. Volume is the number of cubic units contained in a solid. Now our volume congruence postulate says that if two solids are congruent, then they have the same volume. And then more importantly, the volume addition postulate says that the volume of a solid is the sum of the volume of all of its non-overlapping parts. So that means if we don't have a volume formula for a specific solid, we can always cut it into pieces, find the volume of those individually, and then add them back together to find the area of the whole shape. So I have two formulas for you. So the first one is volume of a prism. So volume equals big B times height, where just like in surface area, big B stands for the area of the base. So volume equals big B times height, so area of the base times height. And then volume of a cylinder, just like we talked about before, the volume of a cylinder is going to be just like for a prism, so volume equals big B times height, but we can go ahead and plug in because we know that big B is going to be pi r squared because it's a circle. So my volume of a cylinder is pi r squared height. And that's everything I have for you today. See you in class.